Good afternoon everyone, hope you're all well. It's Dr. Bennett here again, and today we're going to be talking about an extension to what we were discussing in the last class, which was moments of inertia. So today we're going to look at something called the parallel axis theorems. And the parallel axis theorems are useful to us if we know the moments of inertia of an area or a shape about a particular axis in a given coordinate system, and we would like to basically convert that result that we have to find the moment of inertia about a different axis or point. So what I'm going to do in the first part of this tutorial is basically just go over the formulation and derivation of the theorems, and then following that we'll do a couple of examples. So firstly then, suppose we know the moments of inertia of our arbitrary blob of area A about its centroid of its area, right? So all of these results for common shapes are actually given in the textbook in the appendices, right? If you turn to page, what page is this? 577, Appendix B, you will see that for common shapes, let's just take this rectangle here for example. The centroid of its area is given by points x dash, y dash, and then we are given the moments of inertia about that point. Okay, so these are all standard results about the centroid of the area, and they're all given in the textbook. So let's assume that we know the moment of inertia of this arbitrary blob A about its centroid of its area, right? And we call this axis system x dash, y dash. So what we want to do is use that information to work out the moment of inertia of this shape, of this area, about a different axis, right? So here is our original axis system where we know the moment of inertia about x dash, y dash, right? And here is the new axis system, just x, y, which we'd like to find the moment of inertia about. So we're going to use the information we know about the moment of inertia about this axis system and just shift it by this distance d, which can be worked out by a little bit of trigonometry, right? If you know the shift in x and the shift in y. And we're just going to use that information to work out what the new moment of inertia about this shape, about this different axis system. So we know from last time, or from a couple of classes ago, we have formulae, these integral equations for the centroids of the area of a shape. So remember the centroid of the area, the coordinates are given by x bar, y bar, right? But we said, for the example that we're considering, that this coordinate system, x dash, y dash, is at the centroid of the area, right? Remember over here, that's how we defined the x dash, y dash coordinate system. So therefore we know the coordinates of the centroid of the area because that's how we defined it, right? It's at the origin. Yeah. So if that's the case, then if we know x bar dash and y bar dash are both 0, then we can rearrange these equations, right? So we have 0 on the left hand side of both. We can multiply through by this integral in the denominator, and we just get the numerator equal to 0, right? Which is what I've written here. So this just comes from the definition of our coordinate system x dash y dash, and that we defined it at the origin, right? So to calculate the moments of inertia, this is just the formula from last class, right? To find the moment of inertia about the x-axis, we take the integral over a of y squared, right? But now what I've done to y is I've shifted it by this distance dy. So I have the original y position and I've shifted it by dy, right? Remember here. So this is my original y dash, and I've shifted it by distance dy. So that's what I've replaced in this integral equation here. Then I've expanded it, right? I've expanded the brackets to get this. And then I've used the laws of integration just to split this up into 3 separate integrals, right? So I just have the integral of this with respect to a, plus the integral of this with respect to a, plus the integral of this with respect to a. And then to get from here to here, all I've done is just taken the constants out of the middle integral, right? So 2 dy, which is the shift in the y, out of the integral equation to get this. Now, look what we have. This middle term here is 0 because we said up here that the integral over a of y dash is 0, which is what I've got here. So that whole term goes to 0. This over here is just the moment of inertia about the original x dash coordinate system, right? So look at this compared to this. All that's different is that I'm dealing with y dashes instead of y. So this is my moment of inertia about the x dash coordinate system. And then this is just the integral of a constant with respect to a, right? So I just get dy squared a. So what I do is, if I put all of this together and tidy it up a little bit, I just have the moment of inertia about the x-axis is just the moment of inertia about the original axis, x dash, plus this constant here, which is the shift in the y multiplied by the area of the shape. And for common shapes, as we'll see in the examples, this is going to be an easy term to calculate. And the moment of inertia about the y-axis is exactly the same if you follow the same derivation. So these two things in these boxes here are what's called the parallel axis theorems. And as I say, they're useful for calculating the moments of inertia about a new coordinate system, x, y, based on information that we know about the moments of inertia about a different coordinate system, x dash, y dash. So before we get into the examples, just a couple of extensions to that. The first one is about polar moments of inertia. So we discussed last time that we can also find the moments of inertia about a point. We discussed that example where we looked at calculating the moments of inertia about the origin, and we called that the polar moment of inertia, and it's given symbol J0, subscript 0, if we're dealing with moments of inertia about the origin, right? And we showed, or we derived, the equation for this to just be the sum of the moment of inertia about the x-axis plus the moment of inertia about the y-axis. Well, following on from what we were discussing about the parallel axis theorems is, if we basically replace these two terms with what we got from the parallel axis theorems, so these bits, if we replace those in here, we get the moment of inertia about the original coordinate system plus these terms, and if we tidy it up, we get just the polar moment of inertia about the original coordinate system, right, in terms of x dash and y dash, plus these constants here. So that's one thing to note, and that should be fairly intuitive due to how we derived those equations. The second thing, well, the second two things are kind of related, but this seems like a lot of words right now, but you'll see in a second when I've explained this that it's actually quite intuitive, and we'll do an example of both of these as well. But basically, if we have an area that we'd like to find the moments of inertia of, composed of some common shapes, like basically glued together, we can split the total area up into things that we know some information about, common shapes, right, that we can find some details on in the appendix, and we can find the total moment of inertia of the whole area by summing the moments of inertia of the individual pieces, right? So if we have this total area subscript t that's made up of n pieces, we calculate the moments of inertia of the pieces and just add them all together, right? So that's all that says. The next bit is about an area where we have a total area with a piece cut out, and in that case we find the moment of inertia of the total area, and then we find the moment of inertia of the cutout piece separately, and then we just subtract the cutout piece from the total area to find the piece that we're interested in. So that should be quite intuitive, and as I say, we're now going to have a look at an example of both of these things. So this is example 1 then. So we're looking at this compound shape or composite area of these two rectangles glued together. So the first one is 4 meters high by 1 meter wide, and the second one is 2 meters wide by 1 meter high. And we want to find the moment of inertia about the x-axis. So what we do is, as we've just discussed, we split this into two pieces, common shapes that we know how to deal with, right? So we have two rectangles. We know all of the information about that from the appendix in the textbook. So we'll calculate the moment of inertia of both pieces and then add them together, like we just discussed with the compound shapes. So here's the first bit, look. So we just have this one rectangle, 4 meters high by 1 meter wide, and we know the moments of inertia about its centroid of its area, right, from the textbook. So let's go back into Appendix B, find information about rectangles. Okay, so here we have x dash y dash, which give us the coordinates of centroid of the area, and here is our information about the moments of inertia about those two axes, right? So for our example, we're looking at the moments of inertia about the x-axis, so this is the formula that we need. We have 1/12 base times the height cubed to give us our moment of inertia about the centroid. So that's what I've done here. This is a standard result from the textbook as I've summarized here. I just take 1/12 base times the height cubed to get this. So that gives us the moment of inertia about the centroid of the area, but what we want to find, and what the question is asking, is to find the moment of inertia about the x-axis. So we have to apply the parallel axis theorems to deal with this shift, okay? And that distance is what I'm calling dy, right? And I know what that distance dy is, again from the standard results from the textbook, because it tells me that the centroid of the area is just half the distance, right? half h. So that's just going to be 2 meters in our case, right? So I've applied the parallel axis theorems to find the moment of inertia about the new axis, which is x, by applying the parallel axis theorems, right? So you'll remember from what we just discussed, we take the moment of inertia about the old coordinate system and add it to the shift squared multiplied by the area. So in this case, this is the result that we found using the information from the textbook. The shift is 2 meters, right, because it's half of the height, and the area of the rectangle is just the base times the height, right? So if I work that out, I should get 21.33 meters to the 4. So that's the first piece. So now let's deal with the second piece, and this is exactly the same, apart from we just need to recall that the triangle is the opposite, the rectangle is the opposite way around. We have the same formula here for finding the centroid, the moment of inertia about the centroid, and then we apply the parallel axis theorems again to find the moment of inertia of this piece about the x-axis, and then to find the moment of inertia of the total shape about the x-axis. You'll remember that what I just did when I was discussing those extensions was just take the moments of inertia of each piece and add them together. So that should be fairly straightforward and intuitive. So now let's have a look at one final example. So this is now a compound area but with a piece cut out, right? So we kind of have this rectangular piece and then this semicircular piece glued together, but then there's a circular piece cut out, right? And the question is to find the moment of inertia about the y-axis this time, right? Just to give it a bit of variation. So again, we follow the same steps. We'll deal with the rectangle piece first because we just saw an example of that. So it's centered along the x-axis. We need to find the shift in the y-axis, right? That's going to be given by dx. So again, we use the same formula for a rectangle as we saw before. This time we're dealing with the moment of inertia about the y-axis, so we need this. Plug in the information that we have, 1/12 times 80, which is the height, times the base cubed, and I get this. Then apply the parallel axis theorems to take account of the shift. I know that this centroid of the area is half the base, so I should just get 60 squared in here. The area is just given by the base times the height, 120 times by 80, and I should get the following. So that's pretty much exactly the same as the first example. So now let's have a look at the additional pieces. So next we're going to deal with the semicircular piece that's stuck on the end, right? So I've drawn it here with the shift, so I know this is 120 mil. I know the radius is 40 mil from here, and I know the height is 80. So now I need to go back into my appendices and look at information about a semicircle, right? So I need the moment of inertia about the y-axis, and that's going to be given by this formula here, so some constant based on pi multiplied by the radius to the 4. So that's what I have over here, look. that constant based on pi multiplied by the radius to the 4. The radius is 40 mil, so therefore I can calculate this number. And then when I apply the parallel axis theorem, I just need to remember that it's been shifted 120 plus the distance from the edge to the centroid of the area, right? So that's where this term has come from in here. It's 120 mil plus the distance from the edge of the shape to the centroid of the area. Again, I get this from the appendices. So from the edge of the shape to the centroid of the area is just 4r over 3 pi, which is where this number has come from here. And then the area of a semicircle is just half the area of a circle, right? Half pi r squared. So that's where this number comes from. And finally then, we need to deal with the cutout piece, right? The circle. So that's what I've drawn over here. Again, standard results from the textbook. I need to work out what the moment of inertia about the y-axis is, if that's centered on its centroid. Go back into my appendices. Here I go. So I have moment of inertia about y dash, which is the x-axis centered on the centroid of the area, is given by 1/4 pi r to the 4. 1/4 pi r to the 4. Know the radius of the small cutout is 20 mil from here. So then that goes into this formula, and then I apply the parallel axis theorem to deal with the shift. I know it's been shifted to 120 mil, so that's where this term comes from, and then the area of the circle is just pi r squared. So what happens is, when I put all of that together, is that I add, so there's a mistake here that I've just noticed. I add the two pieces that are glued together, the rectangle and the semicircular piece, and then I subtract the moment of inertia due to the circular piece that's been cut out. So actually there's just a little typo, if I can call it that here, where that should be a negative, not a positive. So a lot of action going on outside today. So I add the two moments of inertia of the rectangle and the semicircle together, and then I subtract the cutout piece, and I get the following. So that's it for today. Just a couple of examples on an extension of moments of inertia. Hope you're all staying well, and I look forward to speaking to you all soon. Cheers.